Introduction to Nature's Glow. Hello and welcome. Wherever you are listening from tonight, I'm glad you found your way here. Maybe you're curled up in bed, the room dim and quiet, with only the soft glow of a screen or a distant streetlight slipping through your curtains. Maybe you're wearing headphones on a long, late-night journey, watching the world blur into silhouettes outside a window. Or perhaps you're simply lying still, eyes closed, letting sound be the only light left awake. However you've arrived, this is your time to slow down, to let your breathing soften, your shoulders loosen, and your thoughts drift somewhere deeper and gentler than the day allowed. Tonight, we're going to follow the faintest lights that nature offers. Not the harsh blaze of midday, not the glare of cities, but the delicate glows that appear only when darkness is allowed to settle. We're going to spend time with two very different kinds of radiance, separated by impossible distances, yet strangely similar in spirit. One glows beneath miles of water, where sunlight dies and pressure reigns, shining from the bodies of living creatures who have learned to carry their own lanterns into eternal night. The other glows across unimaginable gulfs of space, born in the hearts of stars and scattered across the sky as ancient messages from far away and long ago. Together, they form a quiet conversation between the deep sea and the deep universe, a twin symphony of bioluminescence and starlight. As you listen, you might imagine your awareness stretching in two directions at once: downward, through the layers of the ocean, past the waves and the bright shallows into blue twilight, then into a blackness so total that the only colors left are the ones life invents for itself. Upward, through the thinning atmosphere, into the chill and stillness beyond, past satellites and the glow of Earth's limb, into a darkness so vast that the glitter of distant stars looks almost like dust on glass. In both directions, a pattern repeats. When darkness becomes nearly absolute, light doesn't vanish. It becomes more meaningful. Every glow matters. Every spark has a story. Bioluminescence, the ability of living organisms to produce light, is one of nature's strangest and most enchanting talents. It is chemistry turned into lanterns, survival written in blue and green, communication expressed as living constellations. Deep sea fish, drifting jellies, tiny plankton, and even some coastal creatures all share this secret, brightening their surroundings with pulses and shimmers that seem almost magical if you see them for the first time. Yet, beneath the wonder, there is nothing supernatural about it. It is molecules meeting in the dark, releasing energy as light instead of heat, a careful reaction tuned by evolution to be just bright enough, just frequent enough to make the difference between feeding and starving, hiding and being found, life and death. Starlight, by contrast, comes from objects that feel almost impossibly far away and impossibly large. Each star you see in the night sky is a sphere of blazing gas, held together by gravity and lit from within by nuclear fusion. At their cores, atoms are pressed so tightly together that they merge, releasing enormous amounts of energy that fight back against collapse. Some of that energy becomes light, streaming outward over millions or billions of years, until a tiny fraction finally reaches your eyes or your camera sensor, or the lens pointed at the sky. We think of stars as distant and static, but the light you see from them is not a frozen picture. It is an ongoing process, a river of photons that began its journey long before you were born, perhaps before your species even existed. On the surface, these two forms of glow could not be more different. One flickers from soft bodies and delicate tissues, from small lives hiding and hunting in cold black water. The other roars from titans of plasma, shining out into emptiness from the hearts of galaxies. One seems fragile and local, the other vast and cosmic. Yet if you listen quietly enough, you can feel a shared pattern beneath them. Both are responses to darkness, answers to emptiness. Both are ways that matter chooses not to remain invisible. Both are signals, whether they're intended to guide a nearby mate or to reveal the composition of a star to a curious mind on a small planet far away. For tonight's journey, you don't need to hold all the details at once. Just let the idea settle that there are two kinds of night we'll be visiting: the night beneath the waves and the night beyond the atmosphere. Each one with its own inhabitants, its own rules, its own language of light. As you drift along with the words, you can imagine different images playing behind your closed eyes or on the screen in front of you. For the moments when we're speaking of the ocean, you might picture dark water, slow currents, faint shapes moving in the distance, and sudden delicate flashes spreading like ink in reverse. For the moments when we're speaking of space, you might imagine star fields, nebulae unfolding like clouds, the silhouette of a planet crossing a glowing horizon, or just a single star hanging in a velvet black sky. The glow of life and the glow of stars are separated by more than distance. They also operate on wildly different scales of time. Bioluminescent flashes can appear and vanish in fractions of a second. A startled fish might light up and dim again in the time it takes you to blink. A drifting jelly might create slow, rolling patterns that travel down its body in smooth waves, lasting a few heartbeats before fading. On the other hand, starlight can persist in a single form for millions or billions of years. A star like our sun spends most of its life in a stable state, its brightness barely changing on human timescales, its light rising and setting every day in a rhythm so familiar, we rarely stop to think about the nuclear furnace making it possible. Yet the photons themselves, those tiny packets of light, still travel one by one, leaving the stellar surface and crossing space until they encounter an eye, a leaf, an atmosphere, or a grain of dust. It is almost comforting to consider that in both cases, light is information. When a bioluminescent animal glows, it is sending a message. Sometimes that message is very direct, like a firefly's flashing invitation or a deep-sea animal's lure, dangling a faint beacon in the water to draw prey closer. Sometimes it is a warning, a sudden bloom of brightness meant to startle or distract a predator. Sometimes it is camouflage, light used not to stand out but to blend in, matching the faint glow from above so that a shadow disappears. Starlight also carries messages, though not ones deliberately sculpted for us. Hidden in the color and intensity and subtle features of a star's light are clues about its temperature, its composition, its motion, and its age. With the right tools, astronomers can read these clues like a quiet, continuous broadcast, decoding what kind of star they're seeing and what might be orbiting around it. As you settle further into this first chapter of our journey, notice how your body responds to the idea of moving between these two extremes. There may be a part of you that feels drawn to the deep sea, to the idea of sinking and being surrounded, of having the world close in until only small circles of light remain. There may be another part that feels drawn upward, toward open vistas and far horizons, toward looking out into a sky with no ceiling. Both impulses are natural. Humans have always been creatures of the in-between, standing where sea meets land, where ground meets sky, where day fades into night. It's no surprise that we are fascinated by what happens when those boundaries stretch to their limits. In later sections, we will separate our path into clearer segments. There will be stretches where we attend only to the ocean's glow, walking among the drifting lanterns of the deep, letting the water and its inhabitants fill our attention completely. There will be other stretches where we leave Earth behind altogether, focusing only on starlight and the cosmic structures that produce it, letting galaxies and nebulae and the soft haze of the Milky Way occupy the entire frame. For now, this first part is simply about settling in, about letting your mind get used to the idea that both realms exist at once, parallel and complementary. You can think of this as the threshold, the place where you sit safely, listening, while doors to two different abysses slowly open. If you were floating on a calm, dark ocean right now, far from cities and their electric brightness, you might see both kinds of glow simultaneously. Look down, and the disturbance of your boat or your hands in the water could stir up microscopic plankton that flash briefly as they're brushed aside, sketching a faint blue trail around you. Look up, and the sky would show its own dotted pattern, with bright stars and dim ones, and perhaps a hazy band of starlight arching overhead if the night were clear enough. In such a moment, you would be positioned exactly between the two worlds we're going to explore. Above, nuclear fusion and gravity. Below, chemistry and evolution. Above, the story of how matter organizes itself on the largest scales. Below, how it organizes itself into fragile, luminous bodies that move and feed and reproduce. You might imagine, as you lie there or sit there listening, that you're in that position now. Not literally on a boat in the middle of the ocean, of course, but figuratively suspended between depths and distances. From this vantage point, the glow of nature becomes a continuum rather than a collection of separate curiosities. The universe seems to have a habit of allowing light to emerge whenever conditions permit it. Together, we will trace some of those conditions. We will look at the molecules that allow a fish to sparkle in the dark without burning itself, and the nuclear reactions that allow a star to shine steadily for billions of years without blowing itself apart. We will ask why so much of natural glow tends to be blue or green, and why starlight is spread into so many colors that, when mixed, seem white to our eyes. We will consider what it means that we ourselves are most comfortable living at a boundary where both types of light can reach us. For now, there is nothing you need to remember, nothing you need to figure out. Let each idea pass the way light passes through clear water or thin air, leaving a soft impression and then gently moving on. Let your breathing find its own pace. Let the muscles around your eyes and jaw loosen a little more. With this first gentle step, we have named the two sources of glow that will guide us: the living lights of the ocean and the stellar lights of the cosmos. In the next part of our journey, we will begin our descent into the deep sea, leaving the surface behind as we follow the first flickers of bioluminescence into the twilight beneath the waves. Sinking past the sunlight, beneath the surface of the ocean, the world changes quickly. If you could slip down through the water as gently as a falling feather, you would notice that the bright, shifting colors near the top begin to soften almost immediately. Above you, the underside of the waves would still glitter with reflections from the sky, a silver ceiling rippling and bending with every swell. Schools of fish might flash in and out of view, their scales catching the light in quick, darting movements. Sunbeams would pierce the surface in long, luminous shafts, reaching down like fingers that grow thinner and weaker with every meter they travel. At first, it would feel as though this light could last forever, but it does not. As you continue to sink, the water around you thickens into deeper tones of blue. Reds and oranges vanish first, swallowed by the water, until anything that once glowed warm instead looks dull and gray. Yellows fade next, then the brighter greens. What remains is a calm, cool blue that gradually darkens, like a sky at the very end of twilight. You may still see silhouettes of larger fish passing some distance away, or the faint suggestion of reef structures, but their details are lost. The world grows simpler, less cluttered, as if someone is slowly dimming the lights in a crowded room, and the chatter of colors is falling silent. This upper region, where sunlight can still reach in meaningful amounts, is where most of the ocean life we typically imagine resides. Coral reefs, seagrass meadows, busy shoals of fish, sea turtles, and rays all make their homes inside this layer of filtered daylight. But for bioluminescence, the truly remarkable displays do not belong here. Sunlight is still strong enough to drown out the softer glows that living things can produce. Even if an animal flashed or shimmered, it would be lost against the ambient brightness, like a candle flickering at noon. For the kind of light we are following, we must go deeper, to places where the sun is no longer the dominant painter of scenes. Descending past about 200 meters, you enter what is often called the twilight zone. The name suits it. Here, the last remnants of daylight barely reach, reduced to a faint bluish haze that never grows brighter, no matter the time of day above. If you were there in person and turned around to look upward, you would see a pale glow marking where the surface must be. A distant ceiling you cannot quite make out clearly. Look sideways, and the water around you would seem dim and empty. Look downward, and the darkness would deepen rapidly, until it becomes indistinguishable from black. It is here, in this half-lit, half-forgotten band of the sea, that bioluminescent life begins to quietly announce itself. At first, the glows might be so subtle that you are not sure whether you have truly seen them. A faint wink of light at the edge of your vision, a tiny spark that appears and vanishes before your brain has finished deciding if it was real. Perhaps a small cluster of dots drifting together, like a patch of moving stars. Much of this light comes from organisms so small, you could hold dozens of them on a single fingertip. Tiny planktonic creatures, floating almost weightless in the water, carry chemical systems that can burst into glow when disturbed. When a larger animal brushes past, a chain of reactions inside their cells releases energy in the form of photons, producing tiny blinks of blue or green. In this way, even a swimmer who cannot see their own hand in front of their face might leave a ghostly trail behind them, outlined by the microscopic lives they have momentarily awakened. If you were to dip your hand into such water on a truly dark night and stir it gently, you might see these sparks for yourself. Each swirl and eddy would seem sprinkled with brief, shimmering stars, swirling in patterns that echo your movements and then dissolve as quickly as they appeared. It can feel like magic, as if the sea itself is responding to your presence. But under the surface, the explanation is quietly precise. The cells of these plankton carry special molecules, often called luciferins, which can release energy as light when they react with oxygen. Other molecules, luciferices, help guide and control this reaction, ensuring it happens only when needed. Together, these components act like a tiny, living chemical switch, one that flips into brightness when touched, shaken, or activated by nerves in more complex animals. The deeper you drift into the twilight zone, the more you begin to realize that bioluminescence here is not a rare trick possessed by a handful of odd creatures. It is a common language. Estimates suggest that the majority of animals living in the midwater zones of the open ocean can produce some kind of light. They do not all glow in the same way or for the same reasons. But light has become such a useful tool in this environment that evolution has rediscovered it again and again. Different lineages of fish, jellies, crustaceans, and worms have all, in their own time, invented bioluminescent systems. What looks like a single phenomenon is actually a chorus of separate solutions to the same problem. How to survive when there is little to see and even less to hide behind. The twilight zone itself offers almost no solid surfaces. There are no forests of coral, no rocky ledges, no comforting caves. The habitat is simply water, stretching in every direction. Food can be scarce, and what does drift by is often scattered and unpredictable. In such conditions, there are three main things a creature must do well: avoid being eaten, find something to eat, and eventually find a partner. Light can help with all three, even if that help sometimes comes in strange and counterintuitive forms. Imagine a small fish living hundreds of meters beneath the surface, where the only natural light comes from the faint glow filtering down from above. To a predator looking up, this fish might appear as a dark shape blocking what little brightness there is, a moving shadow against a dim sky. That shadow is enough to give away its position. To solve this, many midwater animals have evolved special light-producing organs on their undersides, arranged in patterns called photophores. These organs can glow with a strength and color carefully tuned to match the dim light from above. When adjusted just right, they erase the animal's shadow, painting over it with false brightness so that, to an observer below, the creature nearly disappears. This is known as counter-illumination, using light not to stand out, but to stay hidden. To maintain such camouflage, the animal must constantly read its surroundings. As it swims up or down, the brightness and angle of the remaining sunlight change, and the intensity of its own glow must follow. In some species, the fish can even sense the downwelling light with organs on its back and adjust its belly lights automatically, like a living camera always recalibrating exposure. The result is an invisibility cloak crafted not from darkness, but from perfectly matched brightness. It is a quiet reminder that in the deep sea, appearances can be deceptive. Something that glows may actually be trying very hard not to be seen. Of course, not all uses of bioluminescence are subtle. Some are alarmingly bold. Certain shrimp and small fish possess the ability to eject glowing fluid into the water when threatened, releasing a cloud of shimmering light that swirls and blooms like an underwater flare. This sudden burst of brightness can startle predators, momentarily confusing them or ruining their own camouflage. It can also act as a kind of glowing arrow, painting the attacker with light and making it more visible to larger hunters nearby. In this way, the small prey animal effectively calls in reinforcements, turning the element of surprise against the predator. Once the luminous cloud is released, the shrimp or fish can dart away into the surrounding darkness, leaving the glowing distraction behind. Other animals take a more patient approach, using light as a lure. The most iconic example is the anglerfish, living in deeper waters still. But the strategy begins to appear even in the twilight zone. Imagine drifting in near total darkness, where your eyes are adapted to detect the faintest glimmer. Anything that shines at all becomes worth investigating. A small, steady glow may indicate a cluster of plankton, a potential meal. Predators exploit this expectation by carrying their own false signals, tiny lanterns or glowing filaments that sway gently in the water. Curious prey, drawn by the promise of food, approach the light, only to find jaws waiting just behind it. Through all of this, one detail remains consistent. Most of the bioluminescent light produced in the open ocean is blue. There are reasons for this. Blue light travels farther in seawater than other colors, scattering less and being absorbed less quickly. This means that, for the energy spent producing it, blue light offers the best reach. It can be seen from greater distances, giving signals and lures broader appeal. Many deep-sea animals also have eyes that are especially sensitive to blue wavelengths, tuned over millions of years to make the best use of the narrow band of light that still penetrates from above. This shared focus on blue turns much of the twilight ocean into a world where color, as we know it, collapses into a gradient of brightness rather than hue. What matters is not whether a flash is red or purple, but how bright it is, how long it lasts, and what pattern it forms. These patterns can be extraordinarily complex. Some squid and fish are capable of producing coordinated waves of light along their bodies, turning their very skin into a living display. A predator approaching from behind might see a series of glowing spots suddenly race forward along the animal's flanks, confusing its sense of direction and speed. Small plankton drifting in dense layers can be triggered in cascades. One organism's glow activating its neighbors so that a disturbance moves through the water like a luminous echo. To a passing observer, these waves of light might look almost like weather, like distant lightning in a cloud, except that the cloud is made of life. As you imagine these scenes, you may notice how different the deep ocean feels from the world you know on land. Here, light is rare and precious, never taken for granted. On the surface, you can flip a switch and flood a room with brightness. In the twilight sea, every photon comes at a cost. The animals that produce bioluminescence must spend energy building and maintaining the chemical machinery that makes it possible. In an environment where food is scarce, this is not a trivial expense. That they continue to do so in such variety and abundance is a testament to how useful light has become. It is no decorative luxury. It is a tool honed and sharpened by necessity. If you were to overlay this slow descent with video, you might picture the scenes shifting in harmony with the words. At first, wide shots of sunlit waves and shoals of fish, then gradually darker frames, the colors fading until blues dominate. Footage from submersibles could show beams of artificial light cutting through the gloom, revealing small, hovering forms and occasional sudden flashes as startled animals respond. Then the lights from the submersible could dim or switch off altogether, leaving the cameras to capture the natural glows that rise from the dark like stars in reverse, dotting the water around the vehicle with tiny drifting embers. Soon, we will dive deeper still, leaving even the last traces of sunlight behind and entering the realms where bioluminescence is often the only light left. There, in the true midnight of the sea, we will meet some of the more famous and extraordinary bearers of nature's living lanterns. Anglerfish with dangling beacons, jellies that ignite themselves in rings and spirals, and fragile creatures whose bodies seem almost entirely made of light. But for now, allow yourself to linger a little longer in this twilight, this in-between zone where the day above and the darkness below overlap. It is here that the first hints of the ocean's inner glow reveal themselves, soft and fleeting, preparing your eyes and your imagination for the deeper radiance yet to come. Entering the midnight zone. As we descend beyond the twilight zone, there comes a moment when sunlight disappears entirely. There is no gradual fading now, no lingering dimness that might fool the eye into thinking the world could still brighten if you just turned the right direction. Instead, there is a clean threshold, like the final step into a room without windows. Above this depth, around 1,000 meters, the sun still leaves a faint signature. Below it, the ocean enters its true night. Here, the darkness is not simply the absence of light. It is a physical presence, wrapping around you like a cold, endless fabric. Objects do not appear as silhouettes anymore. They simply do not appear until they create or encounter light themselves. If you imagine lowering a camera or submersible into this abyss, the experience would feel like drifting into a void that has no floor, no walls, no horizon. The darkness is so complete that even your sense of scale dissolves. You no longer know whether the fish that just drifted past was the size of your hand or the size of your torso. Without light as an anchor, your brain has little to measure with. Yet this midnight zone is not empty. It is astonishingly alive, home to creatures adapted so perfectly to the dark that they seem crafted out of the night itself. Many of these beings are transparent, allowing what little light exists to pass straight through them. Others are jet black or deep red, colors chosen not for decoration, but for invisibility, because red light does not penetrate seawater and thus appears effectively black here. But among this quiet tapestry of shadows, the true lights of the deep begin to shine in earnest. Bioluminescence becomes the dominant visual language of the midnight zone. Tiny drifting animals blink like wandering embers. Larger predators carry glowing spots positioned like lanterns. Some animals produce long, trailing lines of light that unfurl behind them like cosmic contrails, drifting far after the creature itself has vanished into the dark. If you could hover motionless in this region for hours, your surroundings would resemble an ever-changing star field. Brief, punctuated sparkles, sweeping arcs, drifting clouds, sudden flares, and slow burning pulses. It is an oceanic night sky, continuously rewritten. One of the most mesmerizing creatures here is the siphonophore, a colonial organism related to jellyfish. Some species stretch dozens of meters long, though they are delicate as silk. Their bodies are arranged like living chandeliers, chains of glowing bells, sacs, and tendrils that shimmer in coordinated waves. When disturbed, they erupt into cascades of bioluminescence, each section igniting the next in a flowing dance of blue-green fire. A siphonophore lighting up in the darkness is one of the few natural displays on Earth that rivals the beauty of auroras. Except this is happening silently in pitch-black water, far from any witness. Other creatures use light not to display beauty, but to deliver terror. The stoplight loosejaw, for instance, carries two types of bioluminescence. One is the familiar blue-green glow. The other is a rare red beam, invisibly long to most ocean animals, but detectable by the loosejaw's specially adapted eyes. This red light is its private flashlight, one that allows it to see prey without being seen. It is as if evolution handed this fish a pair of night vision goggles while everyone else remains blind to the wavelength. In the deep sea, knowledge of your surroundings is power, and light, especially invisible light, is the sharpest tool. There are also animals whose bodies resemble galaxies more than living things. Some comb jellies carry rows of tiny plates that refract any light they encounter into shimmering rainbows. Others produce bioluminescent streaks that race along their transparent edges like neon tracing wireframes. When they move, it is as if you are watching light itself figure out how to take shape. Their slow, rhythmic undulations turn the darkness into something soft and mesmerizing, almost meditative. And then there are moments of spectacle that break all subtlety. Certain jellyfish species can erupt into spinning pinwheels of light, their entire bodies flashing in spirals that expand outward before dissolving. Some crustaceans fire jets of glowing chemicals at would-be predators, painting the surrounding water with nebula-like plumes. A startled squid might ignite its entire body in a sudden, brilliant bloom before fading again into invisibility. These displays last only seconds. But in the deep sea, seconds can change everything. Movement in the midnight zone is slow and deliberate. Energy must be conserved. A fish might drift for minutes without moving its fins. A jelly might pulse only occasionally. Yet bioluminescence itself creates movement of perception. You might see a flicker several meters away, then another in a different direction, then a long streak trailing off into the darkness. The water around you becomes a quiet canvas on which countless small lives, each unaware of the larger picture, paint fleeting strokes of brightness. If you were editing footage for this segment, the visuals would shift to true blackness, punctuated only by natural glows. Submersible cameras capturing isolated sparks. A comb jelly drifting past like a floating galaxy. An angler fish's lure shimmering in slow motion. A siphonophore lighting up in cascading waves. Every shot should feel like an encounter with something both alien and delicate. As you imagine these scenes, remember that everything glowing here does so with purpose. Nothing wastes light. Every photon spent has meaning, whether camouflage, attraction, deception, warning, or communication. In this world, light is not an accessory, but a language, one spoken fluently by creatures that live their entire lives in darkness. Soon we will travel deeper still, past the limits where even the most daring submarines routinely go, into the crushing blackness of the abyssal zone. There, the rules shift again, and the glow of life becomes even stranger. The abyssal realm and living light, descending from the midnight zone into the abyss, is like crossing from a mysterious forest into another world entirely. The transition is subtle at first. No sudden shift of temperature or texture, no visible line in the water. But the darkness seems to thicken, the quiet deepen, the sense of isolation expand. The pressure becomes unimaginable. At these depths, 4,000 meters or more, the force exerted on every square inch is hundreds of times greater than anything we feel on land. Metal groans here. Human-built vessels tremble. And yet, life persists with an elegance that defies expectation. The abyssal plain stretches across the planet like a hidden desert. It is one of Earth's largest habitats, though few ever think of it. Imagine vast, flat expanses of soft sediment, broken occasionally by rocky outcrops or volcanic ridges. No sunlight reaches this region. No plant life grows. The water is near freezing. The scarcity of food means most animals must be efficient, patient, and opportunistic. Bioluminescence in the abyss changes character. In the twilight zone and the midnight zone, much of the glowing is tied to movement. Flashes, blinks, pulses, trails. Here, deeper still, the light becomes slower and more contemplative. Many creatures glow not in quick bursts, but in steady, soft radiance. The displays seem gentler, as though the animals conserve energy by stretching their glow into a longer, quieter hum, rather than frequent short flickers. Some abyssal jellyfish seem to drift like floating lampshades, their bodies forming large, translucent bells that emit a gentle blue glow. They pulse slowly, with an elegance that feels almost unreal, like the breathing of a sleeping giant. Others produce lights along the edges of their bells, forming thin, luminous outlines that flicker when the jelly contracts. The effect is mesmerizing, a drifting halo in a world without horizons. Here we also find creatures like the barrel-eye fish, strange animals with transparent heads and upward-facing eyes encased in fluid-filled capsules. While the barrel eye itself does not produce strong bioluminescence, it lives among creatures that do, and its vision is adapted to detect even the faintest glows above. In footage, its eyes shine like emerald marbles in the dark, reflecting the tiny lights drifting through the water column. Its presence is a reminder that in the deep sea, Glowing is not just about producing light, but also about interpreting it. Some abyssal organisms use steady light as a lure. The deep-sea anglerfish, perhaps the most iconic resident of these depths, carries its lantern on a thin filament that extends from its forehead. The glowing tip sways and dances in the water, mimicking the movements of small prey. In the absolute darkness, this single floating spark is irresistible. Small creatures drawn to the glow approach cautiously, unaware of the massive mouth waiting just behind it. When the jaws snap shut, the light continues to shine. A steady beacon in a moment of sudden violence. Other creatures use bioluminescence defensively. Some deep-sea worms, when threatened, release glowing orbs that detach from their bodies and drift away like burning embers. These luminous decoys confuse predators, buying the worm precious seconds to slip into the darkness. Some sea cucumbers emit glowing mucus when disturbed, a sticky, shining distraction that clings to the attacker and marks it for larger predators. For these slow-moving animals, light is both shield and warning. In this realm, the color blue dominates almost exclusively. But there are rare exceptions, astonishing flashes of green or even red, created by species that have developed unique chemical pathways. A handful of deep-sea dragonfish can produce red light, invisible to most animals but detectable to their specialized eyes. This secret illumination allows them to hunt silently, scanning the darkness with a beam that no one else can see. Imagine holding a flashlight that lights the world only for you, while everyone else remains unaware of your presence. In the abyss, such abilities become powerful advantages. Despite the extreme conditions, the abyss is not static. Slow currents carry nutrients across the plains. Occasional marine snow, tiny particles of organic matter drifting down from above, creates a constant but delicate rain of food. Here and there, carcasses of large animals may fall from upper waters, becoming feasting grounds known as whale falls, where entire ecosystems gather for years. In these temporary oases, bioluminescence becomes a swirling ballet of activity. Shrimp, worms, and fish glow as they feed, creating shimmering clusters of light against the dark sea floor. Visuals for this section would include rare footage from deep-sea submersibles exploring soft sediments, ghostly jellyfish pulsing gently, anglerfish drifting with their lures illuminated, and occasional wide shots of the abyssal plain. A vast, quiet landscape punctuated by small, moving lights. The contrast between stillness and glow becomes the dominant emotion. The deeper you go, the more bioluminescence becomes not just a tool, but the defining feature of the world. It is the equivalent of plants in a forest or sunlight in a meadow, an essential part of the environment. Without the living light of the deep, this realm would be an empty void. With it, the abyss becomes a place of quiet beauty, a world defined not by darkness, but by the delicate persistence of light. In the next chunk, we will reach the deepest regions, the Hadal trenches, where pressure rises beyond imagination, and where some of the most mysterious bioluminescent organisms reside. Here, in depths beyond light, beyond shape, beyond ordinary existence, we discover how nature continues to create glow, even in its most extreme realms. Into the trenches, the Hadal lights. If the abyssal plains feel like a vast, dark desert, then the ocean trenches are their canyons. Deep, narrow wounds in the seafloor where the planet's crust bends and dives back into the earth. These are the Hadal zones, named after Hades, the underworld. They run like secret scars across the globe, hidden in plain sight beneath the surface of the sea. Some trenches plunge deeper than Everest is tall, slicing into the crust with steep, shadowy slopes and crushing pressures that seem almost hostile to the idea of life itself. Imagine standing at the edge of such a trench, if that were possible, and looking down. The seafloor would simply vanish beneath you, dropping away into blackness. If you followed that descent in your mind, you would pass the already extreme conditions of the abyss and push further into depths where the weight of the water above reaches more than 1,000 atmospheres. Any human-sized structure not specifically engineered for this realm would buckle and implode in an instant. Metals deform here. Air compresses into tiny volumes. At these depths, the very concept of emptiness feels heavy. Yet, despite all this, life exists even here. Not in the same abundance as shallower regions, not with the exuberant variety of coral reefs or coastal waters, but in quiet pockets, in small but determined populations. And with that life, once again, comes light. The Hadal trenches are not lit up like the night sky. Their bioluminescence is often more modest, more fleeting, but it is there. A faint, stubborn radiance that seems almost defiant. Small amphipods, shrimp-like crustaceans, scavenge the seafloor and the slopes of the trench walls. Some of these creatures can produce short flashes of light when disturbed. A flare of blue that marks their presence before they scuttle away. In the gloom of a trench, even a single flash can momentarily redraw the geometry of the surroundings, revealing rocks, sediment, and other animals in ghostly silhouette. The steep walls of the trenches create a somewhat different environment from the open abyssal plains. Sediment can slide down into deeper layers, carrying nutrients with it. Occasional disturbances, submarine landslides, tremors, remix the upper layers of mud and debris. In this constantly shifting terrain, organisms must be both resilient and adaptable. Bioluminescence, even here, offers advantages. A brief flash might distract a predator just long enough for a small crustacean to vanish into a crevice. A soft, steady glow from a gelatinous animal might attract passing plankton, guiding food straight to its tentacles. Many of the animals in the trenches are still poorly known. They are hard to reach, harder to study, and often fragile. Bodies adapted to intense pressure tend to fall apart when brought toward the surface. Our understanding comes from scattered observations, camera drops, occasional submersible dives, and a handful of preserved specimens. It is likely that many bioluminescent species here have never been seen by human eyes at all, their lights flickering in solitude across geologic timescales. Imagine for a moment a small deep-sea snailfish, one of the few vertebrates that can live in the deepest trenches. It glides close to the seafloor, its body soft, its bones reduced to flexible support structures rather than rigid frames. Around it, amphipods swarm over tiny patches of organic matter, their movements quick but cautious. Perhaps a gelatinous worm drifts by, its body faintly glowing. A sudden flash erupts as one amphipod brushes against another or is surprised by the fish's approach. The light reflects off nearby particles, illuminating the mud and stones like a faint lightning strike, then vanishes. For the snailfish, such flashes may be signals, evidence of prey or predators, or just the presence of neighbors. For us, they are glimpses into a world that normally remains hidden, even from our tools. The chemistry of bioluminescence does not fundamentally change in the trenches. The same basic pattern persists. Molecules are excited into higher energy states and then release that energy as light when they return to rest. But the way that chemistry is used, the strategies built on top of it, can shift. In these extreme depths, where food is incredibly scarce, the cost of creating light must be balanced carefully against its benefits. There is no room for wasteful displays. A glow that does not increase survival is unlikely to be maintained over evolutionary time. That is why much of the light in the trenches is brief and functional. It tends not to be elaborate or ornate, but direct. A sudden flash, a small, pulsing lure, a short-lived glow. Yet, when these are captured on camera, they feel no less magical than the grand displays of shallower waters. In fact, they may feel more so. Precisely because we know how hard-won every photon must be here. For your video, this section invites some of the deepest and rarest footage available. Landers resting on the trench floor, their lights turned low, recording the approach of translucent fish and swarms of amphipods. Occasionally, a small explosion of brightness as a startled animal releases a luminous secretion. Wide shots showing the seafloor as fine, powdery sediment, with only a few scattered rocks and the occasional moving shape. The sense you want to convey is one of isolation, but not emptiness. There is life here. It is simply quiet, deliberate, and almost shy. One of the most haunting ideas about the Hadal realm is how old it is. Trenches shift and move as tectonic plates collide and dive. But for millions of years, there have always been deep zones in the ocean, domains where pressure and darkness rule. Bioluminescence in these regions may represent some of the longest-running biological traditions on Earth. Life producing light in darkness, generation after generation, long before humans ever wondered what lay below the waves. To consider that glowing amphipods were startling one another in trench darkness tens of millions of years ago, while dinosaurs still walked the continents, is to recognize just how persistent and unassuming this natural glow truly is. As you let the thought of these ancient, hidden lights settle in your mind, you might begin to notice a subtle connection to starlight. Stars, too, have been shining for billions of years, their radiation crossing the universe long before our planet cooled. In both cases, light becomes a kind of continuity, a thread that ties distant ages together. When we eventually turn our attention upward to starlight and galaxies, the deep sea lights of the trenches will echo quietly in the back of your memory. For now, though, we remain below. We have followed bioluminescence from the faint first glimmers of the twilight zone down into the midnight depths and now into the quiet, crushing stillness of the trenches. We have seen it used as camouflage, weapon, lure, signal, and shield. In the next segment, we will pause our descent and look more closely at the underlying science, at the chemistry and physics that make bioluminescence possible in the first place, and at how similar and different it is from the other kinds of light we know. Coastal glows, human encounters, and myths. Although much of bioluminescence unfolds far from human eyes, in deep pelagic waters and abyssal plains, there are times and places where it reaches out to meet us. These are the nights when shorelines, bays, and lagoons drift into an otherworldly state. Waves igniting with blue fire, swimmers leaving gleaming halos, and every splash drawing a bright signature on the surface of the sea. For people who witness it, even once, the memory often lingers for a lifetime. Imagine walking along a quiet beach on a moonless night. The sky above is dark, pin-pricked with distant stars. The air is still, with only the soft rush of waves sliding up and down the sand. At first, the ocean looks like a black mirror, reflecting only a faint edge of starlight. Then, as a wave breaks, you notice a strange, electric glow tracing its crest. a band of shifting neon blue that appears just as the water curls and collapses, then vanishes as it retreats. Another wave follows with the same luminous edge, then another. The more you watch, the clearer it becomes. The sea is glowing. If you wade into such water and move your hands through it, you might see light blossom around your fingers, outlining them with a delicate halo. Kick your feet, and ghostly trails appear, following each motion. Even small droplets thrown into the air may sparkle as they arc and fall, their surfaces igniting with faint flashes as they hit the water again. It's easy, in such a moment, to feel as though you are standing in the middle of a fantasy, some magic spell having temporarily altered the rules of the world. But the cause is, once again, tiny living things responding to disturbance. Many coastal glows are caused by dense blooms of dinoflagellates, single-celled plankton capable of producing light when mechanically stimulated. Inside their minuscule bodies, a rapid biochemical reaction takes place when they are jostled, generating a brief flash that lasts only a fraction of a second. Multiply that single flash by millions of cells suspended in a wave, and you get a line of light sharp enough to outline the shape and speed of the breaking water. These organisms do not glow for us. Their bioluminescence may serve to deter predators, startling larger animals or attracting attention from still larger hunters who might attack the attackers. But we happen to be large, moving objects as well. And when we run through the surf or drag our oars, we trigger the same reactions. It feels personal, but it is simply physics and biology meeting in a beautiful coincidence. For video, this section invites footage of glowing shorelines, waves with neon edges rolling in near cliffs or sandy bays, silhouettes of swimmers creating luminous outlines, canoe paddles leaving sharp blue trails. From above, filmed by drones, such scenes can look like veins of light pulsing along the water's edge, or like a slow-moving lightning tracing the shore. Throughout history, such phenomena have fed into human myths and stories. Sailors once spoke of milky seas, vast patches of faintly glowing ocean that seem to emit a steady, uniform light over enormous areas. Ships passing through these regions describe the water as looking like a glowing field of snow or a luminous fog stretching to the horizon. Modern science suggests that these may be caused by large concentrations of bioluminescent bacteria activated under specific conditions. But before this explanation was proposed, people imagined all kinds of sources: spirits in the water, underwater fires, or signs from gods and monsters. Even closer to home, glowing shorelines have inspired folklore of their own. In some cultures, the appearance of bright, blue glowing waves has been seen as a sign of the presence of ghostly armies, sea spirits, or supernatural energy. It is easy to feel why, especially if you put yourself into the mindset of someone who has never heard the word plankton or bioluminescence. To see the sea spontaneously light up, answering your touch with sparks, would suggest a kind of listening, a kind of awareness, even if that awareness is actually a chemical reflex. From a scientific perspective, the study of bioluminescence has grown slowly but steadily as our ability to visit the deep ocean and analyze tiny organisms has improved. Early descriptions of glowing seas date back centuries, written by explorers and naturalists who had only their senses and simple instruments. Later, as microscopes and chemical methods developed, researchers began isolating the glowing components from jellyfish, fireflies, and bacteria. The luciferase systems that we now describe were once mysteries. Their existence hinted at decades before their mechanisms were fully understood. Interestingly, the same tools that animals use to glow have become tools for us as well. Certain bioluminescent proteins, such as those found in jellyfish and other organisms, have been adapted into powerful markers in biological research. Scientists can attach these proteins to specific molecules inside cells and track them by their glow, using light as a tracer to follow processes that would otherwise be invisible. In this way, nature's own chemistry of light, honed in the deep sea and other environments, has become part of the way we understand life at the microscopic level. This connection between wild ocean and human laboratory adds another dimension to our appreciation of bioluminescence. The living lights that once seemed like marine magic have become part of our practical toolkit. Yet, even as we harness these molecules for research, the original displays remain undeniably enchanting. A wave lighting up at night is not less beautiful because we know it arises from dinoflagellate chemistry. If anything, understanding that each spark represents the reaction of countless tiny cells makes the spectacle feel even more intricate and alive. You might imagine a sequence here where the documentary transitions from glowing waves at the shore to footage of scientists in dimly lit labs, carefully pipetting luminous solutions into glass dishes. Microscopic images show glowing cells, their internal structures outlined by light. Then, the camera returns to the ocean, where a swimmer's hand carves through the dark water and leaves a radiant trail behind. The scenes mirror each other, light in a dish, light in a wave, both born from similar principles. As we approach the end of our deep-sea-focused section of this journey, it becomes clear that bioluminescence is not just a deep, hidden phenomenon. It is a thread woven through multiple layers of the ocean, from the trenches and abyssal plains all the way to the surf zones where children play. It touches ecology, evolution, behavior, and even human emotion and imagination. It is both practical and poetic, both tool and spectacle. Soon, we will complete our time with the sea and turn fully to the sky. The next chunks will gently bridge our understanding of living light into the realm of starlight. We will see how the same universe that allows shrimp, jellies, and bacteria to glow in water also fuels stars to shine in space. Before we make that transition, we will spend just a bit more time reflecting on what bioluminescence means for life on Earth as a whole. A final, quiet look at the ocean's glow before we lift our eyes to the stars. Reflections in darkness and a glance upward. As we linger at the edge of our time in the deep ocean, it is worth pausing to let the images settle. Flickers in the twilight, steady glows in the abyss, brief flares in the trenches, waves lighting up at the shore. Each of these scenes is a facet of the same phenomenon. Life, faced with darkness, has chosen not simply to endure it, but to respond in kind, generating its own radiance. The result is a world where light is not an external condition, but something created, controlled, and shaped from within. Darkness, in our everyday experience, often carries a sense of absence. When the lights go out in a room, you may feel that something important has been taken away. Details vanish, colors flatten, movement becomes uncertain. But in the deep sea, darkness is the default. It is not a loss. It is the backdrop upon which life paints its stories. Without that backdrop, bioluminescence would be washed out, its messages lost in the glare. In a way, the deep sea reminds us that darkness can be a collaborator rather than an enemy. It provides the contrast that makes light meaningful. Bioluminescence also invites us to rethink what it means to be visible. On land, being seen is often a function of external circumstances, where the sun is, whether lights are on, how clear the air is. In the deep sea, being seen is more often a choice. A fish can reveal or hide itself by turning its lights on or off, brightening them, or changing their pattern. A jelly can become a beacon or a ghost. A shrimp can suddenly mark itself and its attacker in a glowing cloud, then disappear. Visibility becomes not merely a passive state, but an active decision, an ongoing negotiation with the environment and with other organisms. There is something strangely human in this idea, even though the lives involved are so different from ours. We too, in our own ways, decide how and when to make ourselves visible, through words, actions, and the signals we send to others. We shine figuratively when we wish to attract, impress, or connect, and we retreat into metaphorical darkness when we wish to hide or be left alone. Bioluminescent animals do not think of these choices as we do, but the parallels are still striking. Light becomes a language as well as a tool, and to live in the deep sea is to become fluent in when to speak with it and when to remain silent. From a sensory perspective, bioluminescence also highlights how much of reality depends on our tools of perception. For most of human history, the deep sea was known only through imagination and rare, indirect hints. People heard tales of glowing foam, strange lights trailing ships, and mysterious luminous patches in the ocean. Without the ability to dive deep or to carry sensitive cameras, those stories stood half in science and half in myth. Now, with submersibles and instruments that can see what our eyes cannot, we have uncovered a world that was always there, just beyond our sensory reach. It is easy to forget that our eyes only capture a tiny slice of the electromagnetic spectrum. We happen to see roughly the range of wavelengths that penetrate air and water efficiently, and that our ancestors needed to navigate their world. But light continues beyond what we can see, into infrared, ultraviolet, radio, X-rays, and more. Many animals perceive different parts of this spectrum. Bees see patterns in flowers in ultraviolet. Some snakes detect infrared heat. Deep sea fish might be exquisitely sensitive to narrow bands of blue or red that are invisible to us. Bioluminescence brings some of these otherwise hidden wavelengths into view, but it also hints at the vastness of what remains unseen. This awareness prepares us well for the next phase of our journey into Starlight. Just as the deep sea required us to expand our sense of what night can be, the cosmos will ask us to expand our sense of what light can mean on grander scales. Starlight spans a huge array of wavelengths, much of it invisible to our eyes. Astronomers use telescopes tuned to different bands of the spectrum, optical, infrared, radio, X-ray, to reveal structures and phenomena that would otherwise remain hidden. In both deep ocean and deep space, the universe is asking us to become better listeners, to build tools that can detect the faintest whispers of photons. If you picture a scene to capture this moment of transition, it might be a shot at the ocean's surface on a calm night. The camera sits low, half submerged, so that the lower part of the frame shows the dark water and the upper part shows the sky. Gently, small waves roll past, each one with a subtle blue glow along its crest as bioluminescent plankton respond to the movement. Above, stars are beginning to appear in the sky. At first a few, then many, the Milky Way slowly revealing itself as your eyes adjust. For a few breaths, both worlds of glow are visible at once. The living light under the water and the stellar light above. In that single image, the themes of this documentary converge. Down below, light is created by chemical reactions in tiny cells and specialized organs, used for survival, communication, and deception. Up above, light is born from nuclear fusion in the hearts of distant suns, traveling across emptiness for years or millennia before touching the ocean's surface. Both kinds of light are part of the same physical reality. Both are made of photons. Both are governed by the same fundamental laws of energy and matter. Yet one feels intimate and biological, while the other feels vast and cosmic. As you breathe with this image in mind, you may notice a sense of continuity. The bioluminescent glow that marks a wave is, in a distant way, a descendant of starlight. The energy that powers those tiny chemical reactions ultimately traces back to the sun, whose radiation drives photosynthesis in plankton and plants, building the organic molecules that animals later consume. Without starlight, there would be no life as we know it on Earth, and thus no bioluminescence either. The deep sea's living lamps are, in a sense, the universe's own light repurposed into new forms, captured and released again in different contexts. This idea that all light on Earth is ultimately borrowed from cosmic processes is a gentle bridge to what comes next. In the following chunks, we will leave the ocean's depths and travel upward into the realm of stars. We will explore how starlight is born, how it moves, what it reveals about the universe, and how it shapes worlds. We will find that stars, like bioluminescent creatures, have life cycles, changes, and personalities. They too can be steady or explosive, dim or blindingly bright, solitary or part of intricate systems. For your video, the transition from this deep-sea segment to the space segment could be handled with a slow pan from water to sky, or a dissolve from glowing waves to star fields. The voice that has been narrating the quiet of the ocean will now guide the viewer through the quiet of space, carrying with it the calm, slow, reflective tone already established. The topic will shift, but the mood will remain. We are still talking about glow in darkness, still tracing the paths of photons through the void. We are simply zooming out. As this final deep-sea focused chapter closes, let your mind rest on the knowledge that beneath you, right now, the ocean is dark but not empty of light. Somewhere in the midnight zone, a jelly is pulsing softly. Somewhere on an abyssal plain, small glowing creatures are feeding. Somewhere along a distant shore, waves are preparing to light up if someone happens to walk through them. The sea holds its own constellations, unseen but enduring. And now, with that understanding tucked gently into place, we are ready to look up and meet the constellations in the sky. As you listen, you don't need to hold all of this in sharp focus. Let it drift in the background of your thoughts, like the faint light of distant stars. This chunk of our journey is about arriving, about lifting your gaze from the waves you've been watching and allowing the sky to come into view. We are not yet diving into the detailed physics of how stars shine or how galaxies form. That will come. For now, it is enough to simply stand under the night sky in your imagination, feeling its quiet presence. If you close your eyes, you might picture yourself lying on your back somewhere far from city lights. The air is cool. The ground is steady beneath you. The smell of salt from the ocean, or of earth and grass, lingers in the air. Above, the stars shine steadily, unblinking in the thin upper atmosphere. Perhaps a faint streak marks a meteor burning up. Perhaps a satellite glides slowly, reflecting sunlight long after sunset. Each of these is a trace of light in motion, a reminder that the sky is not static, but alive in its own way. In the next chunk, we will gently move closer to one of these stars. Not physically, of course, but in understanding. We will explore how a star is built, how it holds itself together, and how it manages the astonishing feat of shining steadily for millions or billions of years. Just as we once peered into the chemistry of bioluminescence, we will now peer into the physics of starlight. tracing the path from chaotic nuclear reactions at a star's core to the soft, steady glow that reaches our eyes and lights our world. For now, let the stars above you remain as simple points of light, scattered across a velvet darkness. Let the memory of glowing waves beneath you blend with the constellations overhead. You are about to step from one kind of glow into another, carrying with you an appreciation for light as something both intimate and cosmic, as much a part of living creatures as it is a feature of the universe itself. Stars shine. Fusion and photons. To understand starlight, we must start not with the light itself, but with the star as a whole, an immense self-contained world of gas held together by gravity and kept alive by a delicate balance of forces. Imagine for a moment that we could peel away the darkness of space and put a single star in front of you. Not at its true size, which would be overwhelming, but scaled down in your mind. You might picture a luminous sphere, intense and blinding at its surface, radiating light and heat in all directions. That surface, though, is only the outermost layer. The story of the light begins far deeper within. A star like our sun is made mostly of hydrogen, the simplest and most abundant element in the universe. Under the immense weight of the star's own gravity, this hydrogen is compressed into a state very different from the gas we are familiar with on Earth. In the core, temperatures soar to millions of degrees, and pressures become crushing. At these extremes, hydrogen atoms do not behave like separate, gentle particles drifting through air. Their electrons are stripped away, leaving bare nuclei, a dense, seething plasma where particles move at extraordinary speeds, colliding over and over again. In such conditions, something remarkable becomes possible: nuclear fusion. Ordinarily, atomic nuclei repel each other. They are all positively charged, and like charges push away. But in a stellar core, collisions are so energetic and the density so high that occasionally two hydrogen nuclei, protons, come close enough that a different force takes over. This is the strong nuclear force, which, at very short distances, is powerful enough to overcome the electrical repulsion and bind particles together. When that happens, two protons can fuse, starting a chain of reactions that ultimately turns hydrogen into helium. Each time fusion occurs, a small amount of mass is converted into energy, according to Einstein's famous relation between mass and energy. That energy appears in various forms: kinetic energy of particles, gamma-ray photons, and is the source of the star's luminosity. What's astonishing is that even though the mass lost in each individual reaction is tiny, the sheer number of reactions occurring in a star's core is so immense that the total energy output is enormous. Our sun, for example, converts millions of tons of matter into energy every second, shining steadily while barely changing its total mass over human timescales. If you imagine this at a more visual level, you might picture the core of a star as a roiling, luminous region, filled with countless particles darting about, colliding, and occasionally merging. Each fusion event is like a microscopic flare, releasing high-energy photons. These photons do not immediately burst out into space. Instead, they begin a long, meandering journey outward through the star's interior. The path from core to surface is not straightforward. The star's interior is crowded with particles, ions, electrons, and atoms in various states. As a photon tries to travel outward, it is constantly absorbed, re-emitted, or scattered in new directions. Some estimates suggest that it can take hundreds of thousands of years, or even more, for energy released in the core to make its way to the surface in the form of the light we see. By the time it emerges, the original high-energy gamma rays have been transformed into lower-energy photons spread across the visible and infrared spectrum. This slow diffusion is one of the reasons stars can shine steadily for so long. Energy is not dumped all at once, but filtered gradually through layers of material, smoothing out fluctuations. The outer layers of the star act almost like a buffer, radiating away energy at a rate that balances the inward pull of gravity. If the star were to suddenly emit much more light, it would lose energy too quickly and begin to contract. If it emitted much less, gravity would cause it to compress further, heating the core and increasing fusion rates. Over long timescales, these opposing tendencies find a stable balance. The result is a main sequence star, a star in the long, quiet middle chapter of its life, burning hydrogen to helium with a nearly constant luminosity. When we see starlight from Earth, we are seeing the final stage of this process. Photons that have wandered for ages inside the star's interior stream freely into space once they reach the surface. From there, their path is simple and straight. There is little in the vacuum of space to stop them. They travel outward in all directions, forming an expanding shell of light that grows thinner as it spreads. A tiny fraction of that shell happens to intersect with our planet, where the photons encounter our atmosphere. As starlight enters the atmosphere, some wavelengths are scattered more than others. Blue light, for example, is scattered strongly by air molecules, which is one of the reasons our sky appears blue during the day when the sun is above the horizon. At night, when the sun is hidden, the atmosphere no longer glows with scattered sunlight, and the background darkens enough for other stars to appear. Their photons, after traveling for years through vacuum, now make their final journey through a relatively thin layer of air, refracted slightly, twinkling subtly as pockets of air move and shift. When that light finally reaches your eyes, it triggers tiny chemical changes in the cells of your retina. Photons strike molecules in your photoreceptor cells, causing them to change shape. This sets off cascades of signals that travel along nerves to your brain, where they are interpreted as points of light against darkness. In this moment, the story of the photon ends as your experience of starlight begins. The energy released long ago in a star's core finds its way into your awareness as a simple, quiet visual impression. The path from nuclear furnace to human perception is long and complex. Yet the result feels effortless, a star simply shining in the night. Different stars shine with different colors and intensities, depending on their mass, temperature, and age. A cooler star might glow more red, its surface temperature lower, its spectrum shifted toward longer wavelengths. A hotter star might blaze blue-white, its surface searing at tens of thousands of degrees. When you look at a patch of sky rich in stars, you are not seeing identical objects, but a diverse population of suns at different stages of their lives. Some are just beginning to burn hydrogen steadily, still settling into their main sequence phase. Others are nearing the end, expanding into red giants or contracting into denser forms. In this way, the night sky is an archive of stellar evolution written in light. Astronomers classify stars into types based on their spectra and temperatures, placing them on diagrams that reveal patterns in their life cycles. Although we cannot watch an individual star age in real time, its changes unfold far too slowly on human timescales. We can infer the story by studying many stars at different points along that path. Bioluminescent creatures in the deep sea have life cycles measured in months or years. Stars have life cycles measured in millions or billions of years. Yet in both cases, glow is a sign of an underlying process. Metabolism in one, fusion in the other. If you imagine a sequence of visuals for this section, it might begin with a quiet, wide shot of the night sky, then slowly zoom toward a single star, its light growing brighter. The view could shift to an artistic cross-section of the star, revealing layers: core, radiative zone, convective zone, surface, each with swirling motions and particle interactions. Abstract animations could show nuclei fusing, gamma ray scattering, photons turning into lower energy light, and finally streaming into space. Then the camera might glide back outward, returning to the perspective of a person lying on the ground, seeing that same star as a simple point of light. There is a poetic echo here of the bioluminescence chemistry we explored before. In both deep-sea organisms and stars, light appears when systems move from excited states to calmer ones. The details differ. In a jellyfish, electron energy levels in luciferin molecules shift and relax. In a star, nuclear reactions rearrange nucleons and convert mass to energy. But the idea is the same. Transitions between states give off light. The universe seems to have an inclination, wherever conditions allow, to turn changes in energy into radiance. As you rest with this understanding of how stars shine, there is no need to memorize details of fusion chains or internal structure. Let it be enough to know that the light you see from a star is the end result of an immense, ongoing balancing act. A star holding itself together against collapse by releasing just enough energy to push back. That energy, carried outward as light, eventually washes over planets, warms surfaces, drives weather, fuels life, and in some cases, inspires beings to look back at its source and wonder. In the next chunks, we will explore how starlight interacts with its surroundings, how it shapes the worlds that orbit stars, and how, when we look deeper into space, we see entire galaxies glowing with the combined light of billions of suns. We will also begin to draw more explicit connections between the glow of stars and the glow we saw in the ocean, tracing how energy from one ultimately supports the other. For now, as you breathe in and out, imagine the sky above you as filled not just with distant points, but with long journeys of photons finally coming to rest in your gaze, each one a tiny messenger from a furnace you will never visit, yet whose light touches you all the same. Stellar colors, temperatures, and the language of light. As we move deeper into the realm of starlight, the sky that once looked like a scattered field of identical points begins to reveal its subtleties. Stand outside on a clear night and look long enough, and you may notice something you didn't before. Not all stars shine the same way. Some shimmer with a cooler, golden tint. Others gleam icy blue-white. A few, though faint, appear almost orange or red. These differences, though gentle to the eye, tell rich stories about what is happening inside each star. A star's color is not an accident. It is a direct consequence of its temperature, just as heated metal glows dull red before turning orange, then yellow, then white as it grows hotter. A star follows the same rule, but on a scale far beyond earthly experience. Cooler stars, with surface temperatures around 3,000 degrees Celsius, glow in warmer hues, deep oranges and reds. Hotter stars, with surfaces heated to 10,000 degrees or more, shine in pale blues. Our own sun sits comfortably in the middle, emitting a warm, balanced light that appears yellowish-white from Earth. If you imagine the night sky arranged by color instead of brightness, it would look like a subtle rainbow painted across the darkness. The reddish stars are typically smaller, older, and more stable than their hotter blue counterparts. The blue stars, though dazzling, live fast and die young. Their intense heat and enormous luminosity drain their fuel quickly, burning through hydrogen at rates many times that of the sun. Their lives may last only tens of millions of years, a brief flare when measured against cosmic time. When astronomers study starlight, they do not just look at color. They spread that light out into its component wavelengths, much like a prism turning white light into a spectrum. Within that spectrum are tiny gaps, dark lines that indicate which elements lie in the star's atmosphere. Hydrogen, helium, calcium, sodium, iron, each leaves its signature. These lines allow us to read a star's composition from trillions of kilometers away. We cannot touch a star. We cannot scoop a sample from its surface. But by studying how starlight is absorbed and altered as it passes through stellar gases, we can learn what that star is made of. This idea may remind you of something from the deep sea. There, bioluminescence reveals behavior, flashes indicating movement, communication, or escape. Here, starlight reveals structure, chemical fingerprints embedded in beams of light. In both places, light is not just illumination. It is information, encoded and waiting for whoever has the tools and patience to decode it. Consider for a moment how remarkable this is. A star burns so fiercely that its radiation travels across unimaginable distances, reaching Earth after crossing empty space unchanged. That light carries with it messages from the star's atmosphere, its temperature, its chemical composition, its motion. Even the Doppler shift, the stretching or compressing of wavelengths, can reveal whether a star is moving toward us or away. All of this contained within a single beam of starlight. If you picture this visually, imagine a lone star floating in a dark expanse. From its surface, streams of light radiate outward like threads, extending into infinite space. One of those threads stretches all the way to your eyes. As the light enters your awareness, it doesn't simply brighten your perception of the night. It whispers details about the star itself, like an ancient traveler reciting a story from its homeland. Some stars pulse, their brightness rising and falling in cycles. These changes in luminosity are not random. They reflect rhythmic expansions and contractions within the star's outer layers. By studying these pulsations, astronomers can learn about the star's internal structure. In a way, such stars are like living beings with heartbeats. Light as pulse, rhythm as the outward sign of an inner life. Others spin rapidly, flinging their atmospheres outward into elongated shapes. Some exist in pairs or groups, orbiting one another in complex dances. When two stars orbit very closely, their lights interlay. The combined glow shifts and dims as each star blocks or reveals the other. A cosmic eclipsing performance that allows astronomers to measure their sizes, masses, and orbits. Everywhere in the sky, these subtle signals are happening all the time. Yet to us, looking up casually from Earth, the stars appear still, steady, almost unchanging. In truth, nothing could be further from reality. Each star is in motion, spinning, orbiting, drifting through the galaxy. Each is aging, consuming fuel, evolving. What we see is but a single frame in an immense cosmic film, captured at the instant our eyes meet their light. This realization adds a quiet dimension to stargazing. It becomes not just an act of looking at lights, but an act of witnessing energy that began its journey long ago, shaped by forces more powerful and enduring than anything we encounter on Earth. We see the glow, but not the furnace. We see the calm, but not the turbulence, and yet the light makes its way to us all the same, offering us glimpses into a world both violent and beautiful. If you let your imagination drift now, you might picture a gentle dissolve from a glowing wave crest to a star of similar hue. The bioluminescent blue of a dinoflagellate bloom transitions into the blue-white glow of a hot star. The connection is not literal, but poetic. Two different forms of light that share the same universe, born from processes vastly different, yet bound by common physics. In the next chunk, we will look more closely at how stars evolve, how they are born from clouds of gas and dust, how they change over time, and how some end their lives in explosive events that scatter new elements into space. Just as the deep sea taught us that light comes in many forms and serves many purposes, the cosmos will teach us that stars, too, live diverse and dramatic lives, each stage marked by a unique glow. For now, let the stars remain points of color against the darkness. Tiny reminders that even across enormous distances, light carries stories, and the universe is full of voices speaking in photons. The life cycle of stars, from birth to brilliance, to understand starlight not just as a momentary glow, but as part of a long, unfolding story, we must step back even farther. A star is not born shining. Its journey begins in darkness, much like the deep sea creatures whose glow emerges as a response to the environment around them. For stars, light comes later, after a slow gathering of material, a rising heat, and a moment when gravity and pressure reach a critical balance. Imagine a vast region of space filled with gas and dust. To the naked eye, such a region might appear as a faint smudge or not at all. But through sensitive telescopes, it becomes clear that these are nurseries, places where the raw ingredients of stars quietly drift, waiting for something to disturb their stillness. These clouds, called molecular clouds, are cold and dense by cosmic standards. Hydrogen atoms, microscopic dust grains, and complex molecules float within them in a delicate balance. The first step in the birth of a star often comes from an external nudge. A nearby supernova explosion might send shockwaves rippling through the cloud. The gravitational pull of the cloud may grow unstable in certain regions, or flows of material from neighboring stars might compress pockets of the cloud. Whatever the cause, a section of the cloud begins to contract under its own gravity, pulling in more and more mass as it tightens. As the material gathers, it heats. The particles collide more frequently, their kinetic energy rising. The growing sphere, still opaque and far from shining like a star, becomes what astronomers call a protostar, a warm, dense core surrounded by a rotating disk of gas and dust. This disk may eventually form planets, moons, asteroids, and other bodies. But that comes later. In these early moments, the protostar is simply feeding, drawing mass inward, building pressure. Inside the protostar, the temperature climbs steadily, millions of degrees, tens of millions. At some critical threshold, the heat becomes intense enough for nuclear fusion to begin. Hydrogen nuclei start to merge into helium, releasing energy. It is at this moment that a star truly ignites, though not in a way that resembles fire. There are no flames, no sparks, only the quiet, persistent start of fusion reactions that turn gravitational collapse into radiant energy. With fusion underway, the protostar becomes a main sequence star. It settles into a long, stable phase, with outward pressure from fusion balancing the inward pull of gravity. This is where most stars spend the majority of their lives. Our sun has been in this phase for about 4.6 billion years and will remain so for billions more. During this time, the star shines steadily, converting hydrogen into helium in its core, radiating energy into space, warming any nearby planets, and shaping the environment around it. But stability is not eternal. Eventually, a star exhausts the hydrogen in its core. When that fuel dwindles, the balance breaks. Gravity begins to win. The core contracts and heats again, triggering new reactions. The outer layers expand dramatically. The star swells into a red giant, its radius growing large enough to engulf planets that once orbited safely. Its light softens into a reddish hue. This vast swelling is gentle compared to what might come later. But from the perspective of nearby worlds, it is catastrophic. For a star like the Sun, the end of the red giant phase occurs when the outer layers are shed into space, forming a glowing shell of gas called a planetary nebula. The remaining core contracts into a white dwarf, a dense, hot ember that slowly cools over billions of years. It is still luminous at first, but without fusion, its light gradually fades. A white dwarf is the quiet end of a sun-like star's story. For more massive stars, the story is far more dramatic. Their cores grow hotter as hydrogen runs out. They begin fusing heavier and heavier elements. Helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each stage occurs faster than the one before. The star becomes layered, like an onion, each shell burning a different element. But this cannot last indefinitely. Iron cannot be fused in a way that releases energy. So when a massive star's core becomes mostly iron, it reaches a dead end. Gravity rushes inward. The core collapses in a fraction of a second. The outer layers crash down, rebound, and are hurled outward in a supernova explosion, one of the most powerful events in the universe. For a brief time, the star outshines entire galaxies. The explosion creates elements heavier than iron: gold, silver, iodine, uranium, scattering them into space, enriching future star systems with the ingredients for worlds and life. The remnant left behind depends on the star's mass. Some collapse into neutron stars, dense, spinning objects with magnetic fields so intense they beam radiation into space like cosmic lighthouses. Others collapse even further into black holes, regions where gravity becomes so strong that not even light can escape. Each stage of a star's life emits light in different ways. Protostars glow with the heat of collapse. Main sequence stars shine steadily with fusion. Red giants radiate more softly, but far more broadly. Supernovae explode with a brilliance unmatched by any biological glow. White dwarfs emit fading heat. Neutron stars pulse. Black holes warp the light around them. Light becomes a record of change, a biography written in illumination. If you visualize this chapter, imagine a sequence beginning with a dark cloud of dust drifting in space, gradually collapsing into a brightening protostar. Then, the scene shifts to a stable star shining for millions of years. It swells into a giant, sheds its layers, and leaves behind a pale, glowing dwarf. Or, in the massive star version, it explodes in breathtaking brilliance, scattering luminous debris into the cosmos. As you let these images settle, you may feel a quiet recognition. Everything around you, your body, your home, the Earth itself, contains atoms forged in the hearts of long-dead stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms the backbone of life. All were created in stellar furnaces and released into space long before Earth existed. You glow, in a sense, with borrowed starlight. In the next chunk, we will explore how starlight interacts with planets, the role it plays in shaping atmospheres, climates, and the conditions for life. Just as the deep sea taught us how organisms shape and respond to light and darkness, the cosmos will show us how worlds evolve under the influence of their stars. Starlight and the worlds it shapes, planets, atmospheres, and the possibility of life. Now that we understand how stars are born, live, and shine, we can turn to the worlds that gather around them. A star is not simply a luminous object in the sky. It is the central engine of an entire system, influencing everything that orbits it. The light a star produces, its brightness, its temperature, its stability, determines the fate of planets, moons, and atmospheres. In this way, starlight becomes not just illumination, but architecture, shaping climates, carving patterns into landscapes, and setting the stage for life. Imagine a newly formed star surrounded by the remnants of its birth cloud, a broad disk of gas and dust encircling it like a flattened ring. Within this disk, tiny particles begin to stick together, forming clumps that grow into rocks, then boulders, then planetary embryos. Over millions of years, these bodies collide, merge, scatter, and settle into orbits as full-fledged planets. The layout of the system depends on many factors: temperature gradients, gravitational interactions, initial mass distributions. But the central influence is always the star. Close to the star, where temperatures are high, lighter elements tend to vaporize. Here, rocky planets form, dense spheres made of iron, silicates, and metals. Farther out, where the disk is cooler, ices and gases remain stable. In these regions, giant planets, worlds like Jupiter or Saturn, take shape, their cores accumulating thick, swirling envelopes of hydrogen and helium. Farther still, in the frigid outer zones of a system, icy bodies form, dwarf planets, comets, and reservoirs of frozen material that may occasionally drift inward, bringing a reminder of the system's distant boundaries. But the story does not end with formation. Starlight continues to sculpt these worlds long after they take shape. Depending on a star's temperature and luminosity, a planet may be warm enough for liquid water, cold enough for permanent ice, or hot enough to boil away its atmosphere. The zone around a star where conditions permit liquid water on a rocky planet's surface is often called the habitable zone. This concept is simple yet profound. It marks the region where a world could, in principle, support life as we know it. Earth sits comfortably in the sun's habitable zone. Our oceans remain liquid, our temperature range moderate, and our atmosphere stable enough to support life. But move Earth closer to the sun, and it would risk becoming more like Venus, a world of crushing heat and dense, toxic atmosphere. Move it farther away, and it might resemble Mars, cold, dry, with only faint memories of liquid water. In this way, starlight acts like a tuning mechanism, setting the broad conditions under which life might emerge or fail. Yet habitability is not only about distance, it is also about atmosphere. Starlight interacts with the gases surrounding a planet, warming them, scattering through them, and in some cases, breaking molecules apart. The greenhouse effect, for example, arises when atmospheric gases trap some of the heat radiated from a planet's surface. Without this effect, Earth would be far colder than it is. With too much of it, the planet overheats. Starlight drives these processes, feeding energy into the system while the atmosphere regulates the balance. On planets orbiting dim red dwarf stars, the story becomes even more interesting. These stars shine with a cooler, reddish light and are far more numerous than stars like our sun. their habitable zones lie close to the star, meaning planets that might support life would orbit tightly, completing years in just days or weeks. Such close orbits often result in tidal locking, where one side of the planet always faces the star, while the other remains in permanent night. The starlight becomes unevenly distributed, scorching one hemisphere, freezing the other, unless atmospheric winds or oceans can redistribute the heat. You might imagine the strange landscape of a tidally locked world. On the day side, the sky burns with the red glow of a nearby star, and the ground may crack beneath relentless heat. On the night side, darkness lasts forever, lit only by faint auroras or distant starlight. But along the terminator, the thin strip between day and night, a world of soft twilight might exist. Here, temperatures could be moderate, winds steady, and conditions suitable for liquid water. Life, if it arose, might cluster in this eternal dusk, shaped by a star that never moves. In systems with hotter, brighter stars, the opposite challenge arises. Their habitable zones lie farther out, but their lifespans are shorter. Massive blue stars burn through their fuel quickly, shining intensely but briefly. Planets in such systems might form, but they may not have enough time to develop life before their star evolves dramatically or dies in an explosion. In this way, starlight becomes a clock. It does not merely warm planets, it sets time limits for their biological potential. Starlight also interacts with planetary atmospheres in ways that reveal a world's secrets to observers far away. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. Molecules in the air absorb certain wavelengths, imprinting their signatures onto the light. By studying these imprints, astronomers can determine what gases are present: oxygen, methane, carbon dioxide, water vapor, and more. In this way, starlight once again becomes a carrier of information, allowing us to infer the climate, chemistry, and even potential habitability of distant worlds. There is a poetic symmetry here. In the deep sea, bioluminescence gives organisms the ability to reveal or conceal themselves. In space, planets reveal themselves through the subtle ways they interact with starlight. A small dip in brightness can indicate a planet's size. A spectral line can reveal its air. A glow can hint at volcanic activity or auroras. Everything, in some sense, becomes legible through the light. If you visualize this, imagine drifting slowly toward a planet orbiting a distant star. As you move closer, the colors change, the shadows shift. You see how the star paints the world, its warmth pooling in valleys, its rays glinting off oceans, its absence freezing polar caps. Then imagine passing behind the planet, seeing only its silhouette edged by a thin, glowing ring of light, its atmosphere scattering the star's rays. In that halo, entire chapters of the planet's story are encoded. Earth has its own ways of using sunlight to shape life. Plants absorb starlight in the form of photons, turning them into chemical energy through photosynthesis. This process, simple yet extraordinary, powers nearly every ecosystem on the planet. Even the deep-sea creatures we explored earlier rely indirectly on sunlight. The nutrients that sink from the surface feed life in the dark, and even bioluminescent organisms trace their energy back to the star we orbit. In this sense, the deep sea's glow is just one link in a long chain that begins with starlight. As you reflect on this, you might imagine a line of light traveling from the sun to Earth, touching the atmosphere, warming the oceans, driving winds, nurturing forests, fueling photosynthesis, feeding fish, feeding plankton blooms, supporting entire food webs, and eventually supplying the chemical building blocks that allow a jellyfish or dinoflagellate to glow in the dark ocean. The beauty of bioluminescence is, in a way, made possible by the beauty of starlight. In the next chunks, we will journey outward still farther. We will look at galaxies, the great cities of stars, and at the cosmic structures that form our universe. Just as we traced how bioluminescence connects the layers of the ocean, we will now see how starlight connects the vast structures of space. But before we leave the realm of individual stars and planets behind, take a moment to appreciate this simple truth. Every world is shaped by the light of its star. Every ocean, every river, every atmosphere, every living thing owes a part of its existence to the ancient, ongoing glow of fusion in some distant core. How starlight builds galaxies, the great cities of the cosmos. As we step even farther outward, leaving behind individual stars and their planets, a new pattern begins to emerge. The night sky that once seemed sprinkled with isolated points now reveals grander structures. Groups of stars cluster together in formations, weaving themselves into immense, swirling assemblies. These are galaxies, the vast cities of the cosmos, each containing billions or even trillions of stars, along with gas, dust, dark matter, and the stories of cosmic evolution written across unimaginable distances. Imagine drifting outward from a single star system like our own. At first, you see the nearby stars, points scattered through dark space, each holding its own retinue of planets. Move farther, and clusters form, small groups of stars bound together by gravity, drifting through the galaxy like neighborhoods in a sprawling metropolis. Continue outward still, and the full shape of the Milky Way comes into view. A barred spiral with sweeping arms, each one a river of starlight curled gracefully in the dark. From this vantage point, starlight no longer belongs to individual suns alone. It becomes a collective glow, a soft haze created by the luminosity of billions of stars blending together. In the deep sea, bioluminescence showed us that many tiny flashes can create an impression of continuous light. Here, the same idea applies on a much larger scale. Each star contributes its own brightness, and together they form the shining disk of our galaxy. A galaxy is not a static structure. It is dynamic, evolving, alive in a cosmic sense. Stars are constantly being born in swirling clouds of gas. Others are dying, exploding, or collapsing into remnants. Starlight marks these cycles, illuminating newborn regions where glowing clouds cradle infant stars, and casting shadows around ancient clusters drifting toward their final stages. In a galaxy, light becomes a map of ages and histories. Bright pockets where new stars ignite, darker patches where dust clouds hide stellar nurseries from view. If you imagine a visual transition here, picture a slow pan across the night sky, from a single star to a crowded star field, then widening into the pale, cloudy band of the Milky Way. The view sharpens, revealing that this band is not a mist, but a dense collection of countless points of light. Pull back even farther, and the Milky Way's spiral structure comes into focus, a great pinwheel floating in darkness. As we drift around the galaxy in thought, we encounter its diverse environments. Some regions are calm and relatively empty, with stars spaced far apart. Others are bustling and chaotic, dense star-forming regions where massive young stars blaze intensely, bathing surrounding gas clouds with radiation. These luminous giants have short lives but powerful influence. Their ultraviolet light ionizes nearby gas, creating glowing nebulae that appear as colorful clouds in astrophotography. Their winds and radiation sculpt the surrounding medium, clearing cavities and triggering new generations of stars. Eventually, when they die in supernovae, they enrich their surroundings with heavy elements, seeding the next wave of planetary systems. In this way, starlight acts as both creator and sculptor. It pushes against gas, shapes clouds, warms dust, and ignites new cycles of evolution. Just as bioluminescence in the deep sea influences behavior and ecosystem structure, starlight influences galactic architecture, guiding the formation and destruction of cosmic environments. Now imagine another galaxy, perhaps a majestic spiral like Andromeda or a compact elliptical glowing with the light of old stars. Each galaxy has its own personality. Spiral galaxies are vibrant, full of young blue stars that burn hot and bright. Ellipticals are smoother, more diffuse, glowing with the softer, redder light of ancient populations. Irregular galaxies, shaped by turbulence or collisions, appear chaotic, their stars strewn unevenly. Yet all galaxies share a common trait. Their structures depend on the interplay between gravity and starlight. Gravity gathers matter, pulling gas into dense regions where stars can form. Starlight then pushes outward, heating, ionizing, and sometimes even blowing gas away. The balance between these opposing forces determines how quickly stars form, how long they live, and how the galaxy evolves. If you picture this visually, imagine vast clouds collapsing into brilliant clusters, then dispersing again under the influence of radiation and shock waves. Over millions of years, these cycles create patterns. Bright lanes, dark rifts, glowing arcs, etched across the galaxy's face. The Milky Way itself is filled with such structures, star-forming regions like the Orion Nebula, glowing supernova remnants, and dark dust lanes that obscure background stars. And then there are the relationships between galaxies. They are not isolated. They drift through the cosmos in groups and clusters, interacting in slow, gravitational dances. Sometimes two galaxies approach one another and merge, their stars swirling together in long, luminous streams. In these collisions, starlight maps the encounter, bright bridges and tidal tails marking where gravitational forces have stretched and pulled stellar populations. Far from being violent in the way we imagine earthly collisions, galactic mergers are more like long embraces lasting billions of years, with stars passing by one another silently, leaving luminous trails in their wake. When galaxies collide, star formation often erupts. Gas clouds compress, igniting new waves of stellar birth. For a time, the galaxy shines more brightly than before, glowing with the combined light of newborn stars. Eventually, the two galaxies settle into a new shape, perhaps a larger spiral, perhaps an elliptical. The light changes, the structure changes, but the continuity of starlight persists. There is a quiet echo here of what we saw in the deep sea. Patterns that persist even as individuals come and go. Systems that maintain identity while renewing themselves constantly. In the ocean, bioluminescence reveals ecological interactions. In the cosmos, starlight reveals gravitational ones. Both act as tracers of processes too large or too slow to observe directly. Now picture drifting farther outward, until the Milky Way becomes just one member of a small group of galaxies, the local group. Beyond that, a cluster. Beyond that, a filament. Starlight becomes not a local phenomenon, but a thread woven into the fabric of the universe. Every glowing point marks a concentration of matter, a step in the hierarchy of cosmic structure. This chunk's purpose is to give you the sense that galaxies, like deep-sea ecosystems, are living systems, enormous, slow-moving, luminous environments shaped by forces that act over vast timescales. Bioluminescence taught us how organisms illuminate the dark waters of Earth. Starlight teaches us how the universe illuminates its own expanse. In the next chunk, we will step even further back and explore the large-scale structure of the cosmos, the cosmic web, and how light travels through it. We will see that just as tiny bioluminescent creatures create patterns in the water, galaxies create patterns on cosmic scales, weaving themselves into a lattice of light and shadow, stretching across billions of light years. The cosmic web. Light across billions of light years. Now let your imagination drift outward once more, far beyond any single galaxy, beyond clusters and superclusters. As your perspective expands, the universe begins to reveal a structure unlike anything in the ocean or on Earth, something both delicate and immense, like a spider's web stretched across infinity. This is the cosmic web, a vast network of filaments composed of galaxies, dark matter, and intergalactic gas woven together by gravity on scales so large that even whole galaxies appear as tiny beads on luminous threads. If you could look at the universe from the outside, an impossible view, but one we can approach through computer simulations, you would not see galaxies scattered randomly. Instead, you would see long, interconnected filaments forming a lattice of light. Between the filaments lie enormous voids, regions so empty that they contain almost no galaxies at all. The universe, on its largest scales, resembles a three-dimensional masterpiece of light and shadow. What binds this structure together is gravity. In the early universe, tiny fluctuations in density grew over billions of years, pulling matter into strands and nodes. Galaxies form along these filaments, flowing toward regions where gravitational pull is strongest. Clusters appear where several filaments meet, glowing like cosmic cities at the crossroads of intergalactic highways. If you imagine watching this unfold in time-lapse, you would see the universe beginning as a nearly uniform fog, then slowly clumping, stretching, and sculpting itself into intricate patterns. Starlight fills the densest regions, making the filaments faintly visible. The dark matter, though invisible, provides the scaffolding on which the luminous parts of the universe gather. There is a parallel here with the deep sea. In the ocean, bioluminescent organisms form patches and patterns, shaping where predators hunt and prey flee. In the universe, galaxies gather into filaments, shaping the motion of matter and the flow of energy on cosmic scales. In both realms, light becomes a tracer of structure far larger than itself. As photons travel across these vast distances, they stretch. The expansion of the universe pulls their wavelengths longer and longer, shifting their color toward the red end of the spectrum. This redshift becomes another carrier of information. The farther a galaxy is, the more its light has been stretched by cosmic expansion. By measuring this shift, astronomers can estimate distances across billions of light years. Imagine a single photon emitted from a distant galaxy. It begins its journey in a place where stars are forming, gas is glowing, and cosmic dust drifts like fine powder. It exits the galaxy, entering intergalactic space, a region of near-perfect emptiness. It travels for millions of years, then hundreds of millions, then billions. Along the way, it passes the faint glow of other galaxies, slides through cold gas clouds, and traverses the dark expanses of cosmic voids. All the while it stretches, its wavelength growing, its energy diminishing slightly, but its message intact. Eventually, after a journey longer than all of human history many times over, the photon reaches Earth. It passes through our atmosphere, enters a telescope, and is recorded as a tiny point of light. In that moment, the universe reveals something about itself. A single photon arriving at a single detector carries information about a place unimaginably distant and a moment unimaginably old. This is the magic of cosmic light. It is not merely illumination, but time travel. When you look at a distant galaxy, you are not seeing it as it is now, but as it was when the light left it, perhaps billions of years ago. You glimpse a younger universe, still forming its structures, still shaping its stars and planets. Light becomes a bridge across time, allowing us to observe eras long vanished. If you picture this visually, imagine drifting through the cosmic web, filaments glowing faintly, galaxies sparkling like fireflies caught in vast strands. Then imagine focusing on one tiny speck of light, a single galaxy far away. A photon leaves it, travels across the web, through voids and past filaments, until it finally reaches your eye. In that instant, the unimaginable becomes intimate. This chunk brings us close to the farthest edges of our conceptual journey. We have moved from glowing plankton to glowing stars, from oceans to galaxies, from bioluminescent flashes to cosmic webs. In the next chunk, we will explore how all of this light, from deep-sea organisms to distant galaxies, connects back to the fundamental physics that governs the universe. We will look at the nature of photons themselves, the fabric of space-time they travel through, and the strange, beautiful laws that allow light to act as both wave and particle. The nature of light, photons, waves, and the fabric of reality. To understand the glow of deep-sea creatures and the shine of distant stars at their most fundamental level, we must travel inward, not into a place, but into the very nature of light itself. Light is something so familiar that we rarely stop to question what it truly is. Yet the more deeply science has investigated it, the stranger and more wondrous it has become. Imagine holding your hand under sunlight filtering through a window. The warmth you feel is carried by photons, tiny packets of energy that have traveled from the sun's surface across 150 million kilometers of space. Now imagine a soft blue glow rising from a wave at night, triggered by bioluminescent plankton. That glow, too, is made of photons, created by chemical reactions inside microscopic organisms. The starlight that shines from galaxies billions of light years away. The glow of jellyfish drifting in the deep, the soft light of a candle. All of these phenomena are made of the same fundamental entities. Photons are not particles in the way rocks or dust are particles. They have no rest mass. They do not occupy space in the same way solid objects do. Instead, they behave like both particles and waves, depending on how we observe them. Sometimes they act like tiny bullets of energy. Other times they spread out like ripples on a pond. This dual nature is not a flaw in our understanding, but an intrinsic part of how the universe works. If you imagine light as a wave, picture a ripple traveling across water. The ripple itself carries energy, but does not require the water to move from one place to another. Similarly, a light wave moves through space, oscillating electric and magnetic fields dancing together in perfect harmony. Even in the vacuum of space, where there is no air, no water, no medium at all, the wave persists. It needs nothing to carry it. It is self-sustaining. If you imagine light as a particle, picture a stream of discrete, indivisible packets, each photon carrying a specific amount of energy. This energy depends on the wavelength of the light. Blue photons carry more energy than red ones. Gamma-ray photons carry far more than visible light, while radio wave photons carry far less. When a bioluminescent organism emits blue-green light, it releases photons of a specific energy determined by its chemistry. When a star emits white light, it releases a broad spectrum of photons of many energies. Remarkably, both descriptions are true. Light is a wave. Light is a particle. These two seemingly contradictory ideas coexist seamlessly. Most of the time, we don't need to think about this duality. But in moments where we examine light closely, measuring its interactions with atoms, observing it in extremely dim conditions, tracking its journey through space, its dual nature becomes essential to understanding what we see. Consider, for example, how light interacts with matter. In the deep sea, bioluminescent organisms control chemical reactions that produce excited molecules with more energy than usual. When these molecules return to a lower energy state, they release photons. The wavelength, or color, of the emitted light depends on the specific molecular structure involved. That is why different animals glow in different shades of blue or green. In stars, photons originate from nuclear reactions in the core. Fusion processes produce high-energy gamma rays that scatter, lose energy, and gradually transform into visible light as they migrate outward. The star's surface temperature determines the spectrum of light it emits. Hotter stars produce more blue photons. Cooler stars produce more red ones. The fact that the same basic particle, a photon, can carry information about both chemical reactions in plankton and nuclear processes in stars speaks to the universality of physical laws. Light is a messenger that does not change its nature regardless of where it originates. It may stretch during its journey, as we saw with cosmic redshift, but its behavior remains consistent across vast scales. Now imagine a photon's journey through space-time. Unlike objects with mass, photons travel at a constant speed, approximately 299,792 kilometers per second. To them, time does not pass in the way it does for us. From the photon's perspective, its journey from a distant galaxy to your eye is instantaneous. Billions of years might pass in the universe. But for the photon, created and absorbed events occur with no separation. This is one of the profound implications of Einstein's theory of relativity. Light experiences the universe differently from everything else. If you picture this visually, imagine a photon being emitted from the surface of a star. It streams outward in a straight line, unaffected by the passage of time as we know it. Yet the path it takes is not always straight in a geometric sense. Gravity bends space-time, and photons follow its curves. Massive objects, stars, galaxies, black holes, warp the space around them, causing light to bend. This gravitational lensing allows astronomers to see distant objects magnified or distorted by intervening masses, much like a glass lens bends light in a terrestrial telescope. In the deep ocean, the path of light is bent by water, particles, and organic matter. In the universe, the path of starlight is bent by gravity. The scale differs, but the principle persists. Photons trace the structure of the environment they move through. The nature of darkness also begins to shift when we consider light this way. Darkness is not the absence of light in a fundamental sense. It is simply the absence of photons reaching our eyes. In the deep sea, darkness reigns not because photons do not exist, but because sunlight cannot penetrate beyond a certain depth. Within that darkness, organisms create their own light. In space, darkness appears where stars and galaxies are sparse, but even there, photons from distant sources continue to travel, faint and stretched, carrying messages across vast voids. The fabric of reality is stitched together with fields and particles that operate according to laws too subtle for our everyday senses. Light happens to be one of the most accessible windows into those laws. It is both simple and mysterious, familiar and alien. It is something we encounter every day, yet its nature challenges our intuition at every turn. At the smallest scales, quantum mechanics governs how light interacts with matter. Photons can be absorbed only in discrete amounts, matching the energy differences between electron levels in atoms. This is why spectral lines appear, unique sets of absorption and emission features that act like fingerprints. When a photon has exactly the right energy to elevate an electron, it is absorbed. When an electron falls back to a lower level, a photon is emitted. These tiny transitions create the patterns we see in both bioluminescent glows and stellar spectra. At the largest scales, relativity governs how light travels through the cosmos. It moves along curved paths in warped space-time, stretches as the universe expands, and provides the most direct evidence of cosmic history. Between these extremes, between quantum mechanics and general relativity, light serves as a bridge, uniting our understanding of the smallest particles and the largest structures. As you rest with these ideas, imagine again the glowing wave crest and the distant star. The photons they release differ in energy, origin, and history. One was born in a chemical reaction inside a plankton cell. The other emerged from a nuclear furnace. Yet, both are manifestations of the same entity, governed by the same laws, traveling through the same universe. In the next chunk, we will explore how light interacts with the most mysterious objects in the cosmos: black holes. These regions bend space-time so severely that not even photons can escape once they cross the event horizon. Yet paradoxically, black holes can also reveal themselves through the way they shape nearby light. Understanding this will bring us to the edge of the known universe and into the deepest mysteries of gravity. Light at the edge of darkness, black holes, and the shadow of gravity. To understand the most mysterious relationship between light and the cosmos, we must approach the one place where light itself reaches its limit, where photons that have traveled freely across billions of light years finally meet a force so intense that they can no longer escape. This place is the black hole, a region of space-time where gravity becomes absolute, where the familiar rules of motion and perception bend toward extremes. Imagine drifting toward a massive star that has reached the end of its life. After exhausting its nuclear fuel, the core collapses under its own weight, shrinking to a point so dense that ordinary matter can no longer support itself. The outer layers may explode outward in a supernova, but the core continues collapsing past every known limit. Eventually, it becomes a singularity, an infinitely small, infinitely dense region where gravity grows without bound. Around this singularity forms the event horizon, a boundary beyond which nothing, not even light, can return. The event horizon is not a physical surface. It is a threshold, a point of no return. Light emitted inside this boundary is drawn inward forever. Light emitted just outside it can still escape, but only if it is aimed outward with enough precision. Even then, the gravity is so strong that photons follow curved paths, spiraling or bending in ways that challenge our intuition. To visualize this, imagine space-time as a flexible sheet. A common analogy, though simplistic: a massive object like a star creates a depression in the sheet. A black hole creates a well so deep and steep that nothing can climb back out. Light, which normally travels in straight lines, curves along this warped surface. Far from the black hole, the curvature is gentle, but as you approach, it deepens rapidly, until even photons aimed sideways spiral inward like water circling a drain. This extreme bending of light gives rise to one of the most striking visual phenomena in the universe: gravitational lensing. When light passes near a black hole, its path distorts, often forming arcs or rings. The most famous of these is the photon ring, a thin circular outline of light formed by photons that orbit the black hole multiple times before escaping. This ring is faint, elusive, and incredibly beautiful. It marks the border between the visible universe and the darkness from which no light returns. You may recall the first image ever captured of a black hole, created by the Event Horizon Telescope. It showed a glowing ring surrounding a dark center, the black hole's shadow. That glow was not the black hole itself, but the light from hot gas swirling around it. The black hole's gravity warped and magnified this light, creating an image unlike anything humanity had seen before. A silhouette carved out of pure gravity. Black holes do not glow, but the environment around them can be intensely luminous. As gas spirals inward, it compresses and heats to enormous temperatures, emitting radiation across the spectrum, from radio waves to X-rays. These accretion disks can be some of the brightest objects in the universe, outshining entire galaxies. Their luminosity is a direct consequence of matter falling into a gravitational well so deep that potential energy converts to light with astonishing efficiency. Yet the contrast between the glowing disk and the dark center remains one of the universe's most powerful images: light surrounding absolute darkness. In the deep sea, we saw creatures using light to survive in a world defined by darkness. In space, we see light tracing the edges of a darkness so perfect that even photons cannot escape it. The parallel is subtle but poetic. Life uses light to navigate the dark. The universe uses light to outline the shape of its most invisible structures. One of the strangest properties of black holes is how they distort time. To an outside observer, an object falling toward the event horizon appears to slow down, fade, and redden, never quite crossing the threshold. The light it emits stretches into longer wavelengths, a process known as gravitational redshift, until it slips out of visibility. From the falling object's perspective, however, time proceeds normally, and it crosses the horizon without any sudden change. This dual experience, two realities shaped by gravity's influence, reminds us that light is not just illumination, but a measure of time and perspective. The deep sea taught us how darkness shapes perception. A black hole teaches us how gravity shapes perception. Light bends, stretches, and transforms in ways that reveal the curvature of space-time itself. If you imagine a visual for this chunk, picture drifting toward a black hole from a safe distance. At first, the background stars appear normal, but as you approach, the starlight warps. Some stars appear smeared into arcs. Others duplicate themselves, their images stretched around the gravitational well. The black hole looks like a sphere of darkness, but around its edge, the photon ring glows. Thin, precise, haunting. Just beyond it, the accretion disk blazes with light from infalling gas. It is motion frozen in brilliance, shaped by forces too immense to comprehend directly. For a moment, imagine the ocean again. A small bioluminescent creature drifts in the dark, releasing a soft glow. Now imagine a black hole, outlined by distorted starlight and the glow of superheated gas. These scenes could not be more different in scale. yet both reveal the same truth. Light always tries to escape the dark, to bring structure and meaning to the spaces it illuminates. Black holes also influence the evolution of galaxies. Supermassive black holes sit at the centers of most galaxies, including our own. Their gravitational pull shapes the orbits of stars and gas. Their jets, immense streams of particles launched from their poles, can heat or scatter the material that might otherwise form new stars. Through these processes, black holes regulate the growth of galaxies, acting as quiet architects of cosmic structure. This is yet another echo of the deep ocean, where certain glowing predators or prey influence the behavior and distribution of surrounding organisms. In the cosmos, black holes do not glow themselves, but the light around them, distorted, amplified, or extinguished, reveals their presence and power. They are the invisible engines of galactic evolution. As we near the end of this chunk, consider how far our journey has taken us. From glowing plankton to stars, from galaxies to the cosmic web, and now to the very edge of space-time. Yet, throughout, one theme remains constant. Light is the thread that weaves these realms together. It is the messenger that carries stories from deep time and distant places. It is the universal signal of energy changing form. And so, we arrive at the edge of our journey, where the last traces of starlight fade into the quiet, and the deep sea and deep space meet in silence. We've drifted through glowing oceans, wandered among ancient stars, followed light across galaxies, and stood at the threshold of a darkness nothing can return from. Wherever you are now, lying down, resting, or simply breathing a little easier, I hope this time has given you space to soften, to drift, to let your thoughts settle like dust in a calm beam of light. Thank you for being here, for listening, for letting this story keep you company tonight. Until next time, rest well, breathe deeply, and let the darkness cradle you gently. Good night.